Good evening all, can you hear me? Okay, is the audio clear? Nothing? Disturbance from my side? Clear, we'll start. So far, before joined, the voice is low, okay, yeah. We'll wait for 2 minutes, then we'll start. Sorry, I forgot to record. No issues, from now onwards I'm recording. Voice is repeating, no, someone has, someone unmuted himself, I don't know. So is it okay now? Okay, we'll go ahead. So what we do is now we try to generate figures using pandas, using pandas library. Okay. Now with the same example, same data set, we'll try to generate, we'll try to produce figures using pandas. So what I do is first, I will import same things. I'm importing this iris data set only. I'm loading the iris data set into iris, right? Now, what I do is this is a NumPy array. You can convert an NumPy array to data frame, right? I hope the data frames, the concept of data frame was discussed. So you can convert this NumPy array into data frame. How to convert this NumPy array into data frame? So let me first import pandas for this. Import pandas as PD. PD is the shortcut name, you know. So let me call this function data frame. Okay, PD dot data frame. So what you have to pass? You have to pass this. So this contains everything. This contains data. This contains target names. This contains target. This contains feature names. Everything. What I wanted to pass is I wanted to pass only iris dot data. Okay. Now let me produce this one first. Let me see. You see? Can you see now? Earlier it was different. Now we have converted that NumPy array into tabular format. These are the names of each and every row. 0. These are the index, you can say. Row index 0, 1, 2, 3, and so on 149. So each row can be accessed using this index, row index. Similarly, you see here, these are the column names, column indexes 0, 1, 2, 3. So if you want to give some separate name for columns, since we have column names, because we have feature names, right? Sepal length, sepal width, petal length, petal width. So rather than writing 0, 1, 2, 3, what I want to do is I wanted to name each and every column. How to do that? We have an option called columns. If you see these columns, what we have to pass for these columns, we have to pass the list of feature names. Oh, how to pass list of feature names? Similarly, simply call iris dot feature names. Now let us see what it will produce. Can you see? This is the column name 1, sepal length, sepal width, petal length, petal width. Is it okay? So we have converted into a data frame. Now let me store this somewhere where I will store same thing with the iris.df. Let me call it. So this is a data frame. It is not an NumPy array. Now it is a data frame, right? Now, is it okay? So I hope this part of uh, data frames was discussed already. And if you want to add some columns, you can add some columns also. Suppose what we have so far, we have iris underscore df. If you see, we have only four features and 150 examples. We have converted into this tabular format. In addition to this data frame, if you want to add some more column, you can add. How to add one more column? Let us say I wanted to add one more column with name group. So this is the fifth, fifth, fifth column I wanted to add it to this data frame with the name group. So what do you mean by group? The target group we have, right? So what do I do? What I do? We have this iris.target. We can access this target list of, so for 150 examples, we have this. Let me first print what is this iris.target. This is the target 150 things, group 0 or group 1 or group 2. So what I wanted to do, I wanted to add new column iris.group, and I want to simply add this iris.target. Okay. So you can add this iris.target, but how to add this iris.target directly? Can you add directly? No. If you want to add one more column, first of all, you have to convert this data into, so first what we have to do, we have to convert this iris.target, this data into some series. Okay. Then you can pass the series here. So pd.series, you can pass a series data here. Series. So you can pass a series here. Okay, some name, series name. So first what I do is I try to convert this series here. So series will take either numpy array or list, whatever you want. So let me convert into list or numpy array. Let me convert into list. Okay. So let me give this list here directly. Okay. Let me pass this list. Iris target of list. Let me see now. It was running. Let me see what is there in iris.df. Now you see, we have added one more column group with the group number 0 or 1 or 2. But instead of writing group numbers, if you want to write group names, that also you can do. How to do that one? Uh, how to give group names rather than group numbers? So first you convert, you replace 0 with, let me first show you iris dot target names. So you replace 0 with Setosa, replace 1 with versicolor, replace 1 with 2 with Virginica. So how to replace that one? So how we can replace that one? How to replace that one? So let us call this something first. Let me call it as a group. Okay. Now if you want to convert this list into list of numbers into list of names. So how to convert? We have something called list comprehension. What is this list comprehension will do? Each number is each in group means it will take each number in the group, then it will see the value. If the value is 0 or 1 or 2, based on that one, it will replace. If the number is, so iris dot target names, if the number is 0, then it will simply access 0th index from iris target name. If the number is 1, it will access first index. You see here, 0 will give you this one, 1 will give you this one, 2 will give you this one. Now you enclose this in list. That's why it is called list comprehension. So you simply take this code here. Instead of groups, you give this one. Now what will happen? Instead of numbers, what will come? Names will come. Now you see what will happen. So the groups are replaced with names. No, all are okay. All I have given 0. So instead of 0, what we should give? We should give I. Now you see, this is Setosa, this is a Vijayanaka. In between there is some color. Have this data frame. Although I have repeated this one because we'll work with this iris dataset. That's why we have converted this iris dataset into data frame. Now we'll try to generate some figures on this dataset, on this data frame. So let me, iris dot target is itself an array. So why we cast it to list explicitly here? Okay. Okay, let me answer this question. Naman, he asked, okay. Yeah, Naman asked some question. Iris dot target itself is an empire array, so why we cast it to list explicitly? Can't we directly put iris dot target names? Okay, iris dot target names itself is okay. That is a good question. So what you was telling is why to do all this? That itself is iris dot or target names. No, iris dot target names. If you see the size of iris dot target names is only 3. CN Kumari, the length of iris dot target names is 3. But how many examples do we have? 150. Each example belongs to one group. Is it okay? No, let me answer first Naman question. Naman asked some question. Yeah. Iris dot target is itself is in an empire, so why we calculate to list text? Yeah, that is true. Why this is required? That's what he was asking. Iris dot target itself is a okay. Now what he wanted to ask is what I have changed something. Control Z, Control Z, Control Z, Control Z. Okay. Now let me store this somewhere. Otherwise, let me delete. Let me. Why it is? What happened? What happened? Oh, this is my control button. Okay. Okay. Now let me delete this one. This list. I will undo. So what he was asking is, if if I pass directly, I reach the target. What happens instead of this one? See, it is all right. Naman, you can directly use group, but if you want to use like this, suppose if you wanted to do this one, I reach the target. Then if you wanted to convert, this is also okay. No need of converting actually. Data frame supports numpy arrays, data frame supports lists, data frame supports dictionaries also. You can use anything. Yeah, this is redundant and actually this statement itself is redundant. What we can do is for in iris dot target, we can directly write. Okay, is it okay, Naman? Okay, so we have removed that one. Yeah, because unnecessarily I have converted. It works with list, it works with numpy array, it works with dictionary. You can use anything. Okay, now other question is, can't we directly put iris dot target names? That is your question, right? Sriyan Kumari. So the problem with that one is, if you see here, iris dot target names, you see the length of iris dot target names, only 3. But how many rows were there? 150 rows. And every row you want group name, this group name. That's why, first of all, we have taken that list of zeros, ones, and twos. Then we have, instead of 0, we have replaced this set aside. Instead of 1, we have replaced this. Instead of 2, we have replaced this. So that is okay. Okay. Yeah, let me post this one also. No need of using list. We can directly use numpy array because it supports, basically data frame supports all. This is directly using numpy array. So now we have generated this iris data frame. Now we'll try to generate some figures from this data frame. Okay. So at the beginning, someone asked how to, somewhere, someone asked how to, let me go there. Let me see. Here x value means row is something. Okay, Karthik asked some question. Okay, let me see here. Okay, x equal to 0, I have explained. Karthik Gaud, you have some question here. X value means where in the first one? Where x value? Oh, here x value means, okay, you're asking this value. I have changed x value to value. So here it is, value means, you see bar graph needs 2 things, this data and this data. So value means this data I'm giving, that's all. And other questions, row wise, yeah, row wise. Okay, you have written, okay. So, and someone else, some asked something about data set. Is that one? How to import data from Excel and draw the graphs for the, more than one data. Okay, that was asked by Venkat. So how to import data from Excel, I hope it was covered in data frames, right? Pandas is that simply pd and pd dot read underscore csv. There is a command called pd. Let me write in chat box, although it is not part of our discussion. Since someone asked, let me tell you. Yeah, Venkat, you have posted. So there is a command called pd dot read underscore csv. You can pass this csv file. Okay, you can directly read this data and import into data frame. Now you can work with data frame. Now whatever we discuss now. Okay. Similarly, you can using pandas, you can import JSON files also. Read underscore JSON, all this. Is it okay, Venkat? Read underscore CSV, read underscore JSON, all these are there. The moment you read that Excel into data frame, you can continue now. Whatever we generate, we can do all those things with that data also. Okay, the same thing. So I am assuming that those reading part, reading CSV, reading JSON files, those were covered in pandas already. That's why I'm starting here directly. Reading inbuilt data set and then converting inbuilt data set into data frame. Now we'll see how to generate some different kind of graphs. So we have already seen this bar chart also. So let us see some other kind of charts with this data frames. So let me show you different ways of generating these graphs on these pandas. I mean, so using these data frames. So suppose if you want to generate some chart, there are many different charts you can draw. So let me first tell you a simple way. Suppose if you want to generate some box plot, call box plot. So this is one way to generate. The other way of generating these figures, I will discuss that one later. So suppose you want to generate a box plot, simply call box plot. So what it will generate? It will generate this. For every feature, it will generate this box plot. This is for feature 1, this is for feature 2, feature 3, feature 4. Now, if you see box plot, those of you who know about box plot, it is all right. For those of you who don't know what is box plot, what these lines represent, here this green value represents average. Average of first feature. We have seen average of first feature is near to 6, right? So this is average. All the green lines represent average of each of their features. Now, what is this line, this line, this line, and this line? 4 more lines are there. What are these lines? So this line is called 75 percentile, this upper line. And this line is called 25 percentile. What is 75 percentile? Mean or average is called 50 percentile. Okay, please remember that this is called 50 percentile. Yeah, this is Q3. Yeah, Q3. This is Q2. This is also called 75 percentile. Q3 means 75 percentile. Q2 means 25 percentile. So this 75 percentile means what? You take all the values that are greater than mean, take all the values that are greater than mean and calculate the mean of them. That will give you 75 percentile. What is 25 percentile? Take all the values that are less than mean and calculate average of those values. That will give you 25 percentile. So this is 50 percentile, this is 25 percentile, this is 75 percentile. Now what are these things? This line and this line. This is 75 percentile plus 1.5 times sigma will give you this line. Sigma means what? Deviation. You calculate standard deviation, add 1.5 times standard deviation to 75 percentile. That will give you this line. What is this? 25 percentile minus 1.5 times sigma will give you this value. Okay. Now, so these are the lines. So in addition to lines, we have these circles. So these circles, yeah, these circles are also called these outliers. What do you mean by outliers? So 75 percentile plus 1.5 times sigma. If there is any value greater than this line, they will be represented with these circles. Yeah, someone posted in chat box also the actual names, whiskers and all those things. Yeah, that is true. Madam as giving the actual values, whiskers, 25 percentile, 75 percentile, all this. Yeah, that's true actually, exactly. So I'm explaining for those of you who don't know. Are outliers or anomaly? Same. Anomaly means some issue, but outliers, okay, in case of data, we may consider outlier and anomaly same. In case of data, anomaly means actually if there is, okay, generally often people use them interchangeably, but there is some difference between this outliers and anomaly. Okay, so for our discussion, we are using this name outlier, that's all. Okay, so this is box plot. So you can directly generate using this command. That's all, box plot. Now, what is the other way? Other way of generating this same box plot? Same thing. We have this command, right? Iris underscore df dot plot command. You simply use plot command. Okay. Then for this plot command, we have to pass the data. Okay, data we have already. Iris dot data, iris dot df dot plot only. So if you see here, oh, it is not now coming. Let me write. Yeah, now it is coming. You see, these are the parameters for this one. Okay. Now if you see, there is an option called kind. What is this kind? The type of plot you wanted to produce. You want to produce line plot, you can produce line plot. If you want to produce bar plot, just now we have produced bar chart, right? Okay, so let me give kind. Kind equals to bar. Okay, I have to give in quotes, bar. This will produce, what it will produce? It will produce bar chart. But it is producing what? It is not producing feature wise. It is producing training wise, means training sample wise. For 150 examples, it has produced. Okay. Suppose if you wanted to produce some other chart, let us say kind equals to, so just now we have seen it will give error. Okay. So this is different plot chart, leave it. Plot, see, you can produce, so by default it has produced line chart for 4 features. This is line chart. Can you see? These are the line chart. Default, if you omit the kind option, it will produce line chart. You can produce bar chart, you can produce horizontal bar, you can produce histogram, you can produce box plot. Just now we have seen, right? Box plot you can produce. All these all these plots you can produce. This is the other way. You can directly call box plot, or you can give box here. Instead of kind, you can give box. So let us produce some charts. Let me produce histogram. So let me give histogram. So you see what it has produced? It has produced 4 histograms because this is sepal length, sepal width, petal length, petal width. That's why it has produced 4 histograms in the same figure. If you want to separate them, you know the option R width equals to 0.9. Let me give 0.9. Then you see this red was here. That means actually this data overlaps. That's why it was coming like this. So let me change this. Let me draw a histogram for a single feature. How to give a single feature? Okay, let me give sepal length and say cm, sepal length cm. So a single feature I am plotting this histogram. So let me paste these things. I have not pasted. You please try to generate these plots. This is box plot. This one with this command you can generate all different kinds of plots, histograms, line charts, all these things, bar charts, horizontal bar charts, box plots also you can generate. So by default, what it will produce? By default, it will produce. You can explore this one also. By default, it will produce line chart. See, for these 150 examples, how the value changing? Change in value. For the first example, it was near 5.2 something. Then it came down to 4 point something, and you see it was changing. The change in values. And using line chart, it was shown. Default, it is line chart. Okay. Now, so So using this kind, you can generate all different kinds of plots. Now let me spend some time on 3D and Seaborn. We have spent enough time on these plottings, different kind of plots. If someone is interested to draw other kind of plots like area charts, pie charts, if you see this option, it will support all these plots. If you see this one, if you see the options kind equals to, you can see the options kind equals to. It supports, you see, it supports area plot, pie plot, all these plots it supports. So you can draw all those plots. So now let me spend some time on 3D visualization. 3D, how to draw 3D graphs. So this matplotlib supports 3D visualization also, 3D figures also. How to draw that one? So first, so initial matplotlib does not support these 3D figures. Later on, they have added some toolkits to support this 3D visualization. So first, let me import this matplotlib. Matplotlib. Okay, now for 3D visualization, if you want to use 3D visualization, there is some toolkit called MPL toolkit. MPL toolkits. In this MPL toolkits library, there is something called mplot 3D. mplot, mpplot 3D. mp, yeah, mplot 3D. Why it is not coming? Yeah, 3D. Yeah. First, let me import. Yeah, it is correct only. So this is the toolkit, MPL toolkits. This is the submodule, mplot 3D. Now, if you want to draw 3D, first let us see. We know this one, plot.figure. What it will do? Plot.figure. We know what it will do. It will initialize the figure, right? We'll give some name. Let us say figure. This we have seen. Similarly, we have seen plot.axis. What it will do? It will initialize axis, but it will initialize only 2 axes, right? If you want to access initialize 3 axes, how we can do that one? There is an option called projection. Give projection as 3D. See now it is producing 3D. Is it okay? So you can give some name here like earlier. You can give these are the axes. So here we have initialized figure. This command is same, but here we have passed this projection equals to 3D. The moment we have passed this one projection equals to 3D, it has produced 3D axis, 3-dimensional axis. Now let me post here. For what iris is used? Iris, okay, let me some command, some okay. For what iris is used? Okay, no, wait, let me. Yeah, for what? Iris is a data set for classification. Suppose you have come up with some classification model and you wanted to test your model on some classification data set, you can use this toy data set. This is with minimum number of examples, 150 data sets, 150 examples, that's all. General data sets will have huge number of training examples. This is a simple minimum data set with 150 examples. Is it okay, Karthik? That's why I have opened in Google, I have shown you, right? sklearn data sets. It was showing all the toy data sets. One data set for regression, right? One data set for classification, wine data set, other data sets also I have shown. Okay, this is how we visualize 3-dimensional axis. Now let us draw one figure in 3D and let us close this 3D visualization. But this 3D supports all different kinds of things. So let us draw some line chart and scatter chart in this 3D. First, let me import these two things. Already once we imported means no need to copy, but let me copy here. Okay, now let me import those things also because 3-dimensional axis we want. Okay, now let me generate some X, Y, and Z data. So similar to 2-dimensional, let me generate some X data. np.linspace, I'm generating 100 samples between 0 and 10. And let me call Y equals to np.sinx. This is the Y data. What is z data? Z data, I'm applying cos function on x values. I think this z data. Now, if you want to plot a three-dimensional line chart, how we can do? Simply call plot 3D. There is a function called plot 3D. Now you pass all these things x, y, and z. You see, earlier we got 2D line. Now what we got is 3D line. Is it okay? So let me post this code. Let me please generate this one. Are you able to see this 3D line on your system? Okay. So now instead of this one, if you want scatter plot, instead of plot, you write scatter 3D. That's all, scatter 3D. Let me generate scatter plot. This is the scatter plot. You see, points are 100. That's why maybe it is more. Let me generate 50 points only. See 50 points. Now it was in 3D, 3 dimension, 3D axis, 3D this one. So this so is it okay? Scatter plot and line plot in 3 dimension. Simple. We are initializing 3D axis. We are calling plot 3D or scatter 3D. You see the options inside plot 3D. You can what? So this 3D visualization MPL toolkits, it supports many other options also. If you want to plot surface plot, there is option called plot underscore surface plot. If you want to draw wire plot, there is option called plot underscore wire plot. So it supports all different kinds of plots. Whatever 3D you want, it supports. You see the options inside plot. This one. Okay. So now let me close this matplotlib. Now let me start one more library called Seaborn. Oh, where is text? This is text one. Okay. Let me call it as Seaborn. Seaborn. Okay. So Seaborn is a visualization library that was built on top of Matplotlib. So it works with Matplotlib. Basically, Matplotlib was built on top of NumPy arrays. This Seaborn was built on top of Matplotlib. So this Seaborn works along with Matplotlib also. Okay, now we'll see how to use this Seaborn for different kind of graphs. Seaborn visualization using Seaborn package. So if you want to use this Seaborn, you simply import Seaborn as some name. You can give whatever name you want. Seaborn, let me give SB. So it works along with Matplotlib also. Let me import Matplotlib also again. Let me give some name. I have imported both Seaborn and Matplotlib. Matplotlib. Okay, now I have imported. Now, suppose you wanted to generate. So, okay, let me bring here some data, X and Y, and all this. Now, if you see, I wanted to generate one figure, plot using X and Y. This is 2D I am generating. So this is the default figure that was produced by this Matplotlib. Now, as I mentioned earlier, this Seaborn works along with Matplotlib. So what I do is I simply call this command called fb.set. Then I call the same thing. Okay, same code after this sb.set. Now can you see the difference in figures? So by default, so this sb.set, what it will do is it will set Seaborn style of visualization instead of Matplotlib style of visualization. So by default, this Seaborn, it will create these things, these grids. It will fill these grids with some shaded color. Can you see all this it has done? So in Matplotlib, you can do this. You can create grids. You can create what? You can create what? You can fill these grids with this color. All this you can do. But for that, you have to write some code. Whereas in Matplotlib, you simply call this command sb.set. Then whatever you print, it will take Seaborn style of visualization. So let me post this code now along with these two commands. Now you will get Seaborn style of visualization. So what this sb.set will do? It will set the visualization to Seaborn style of visualization. Okay. So now we'll see the different other graphs that can be generated using this Seaborn. So we have seen many graphs. We'll see some different graphs using this Seaborn. Okay. So let us try to load some data set using the Seaborn, and then so let me load. So the Seaborn you can you see load data set. There is a command called load data set. So the Seaborn itself supports some simple data sets. So let me call some data set. Is it showing here? Yeah, this is the load data set you see, and you see here. You can go here and you can see what are the different data sets that can be loaded here. Let me load one simple data set called tips. So this data set basically says the amount of tips that was given by customer to the server. Okay, whoever is serving food, he got these many tips. Okay, so this is the total bill. This is one feature. This is the tip he has given, and this is the gender of the customer, whether he is a smoker or not non-smoker. Okay, and on which day he has given, Sunday, Monday, Tuesday, Wednesday, and time, whether it is lunch time or dinner time. Okay, like this. So there are 244 rows were there and 7 columns were there. These are the features. 254, 244 are the rows. Okay, now let me store in something. Let me call it as tips. See, by default, it is loading in data frame format. Can you see? So by default loaded into data frame format. These are the column names. These are the row indexes, right? So let me post this command first. You load from dataset, this dataset. So we have loaded this dataset. Now we'll try to produce some figures using this dataset, but we'll try to generate some different plots. Okay. So box plots, bar charts we produced. So let me produce some other plots. So this Seaborn supports different types of plots called pair plots, factor plots, joint plots, many different plots. So let me produce some plot, factor grid, all this it will produce. So let me produce this factor plot. What this factor plot means, it is like box plot only. Okay. So I have to tell what is x-axis, what is y-axis. So let me tell what is x-axis. I am for day. On what day I got this plot. Okay. I'm producing this. Now for each day and total bill, let us say day versus total bill. Okay. Day versus total bill. Now I have to pass the data also. Where is the data? Data is tips. So let me first produce this one. Okay, what it was saying. Not interpret input total bill. Where is this total bill? Total underscore bill. Okay. Total underscore bill. Data equals to tips. So this is different. Okay. This is with errors it has produced. You see, these are the average values on each day. This is Thursday, Friday, Saturday, Sunday. These are the 4 different days. And this is the bill that was given, the total bill This is the average bill. Okay, this we leave it. So this factor plot, what we can do is we can group it also. Suppose if you want to group it time wise, whether it is lunch or dinner. Okay, it is giving factor plot or factor grid. Factor plot only. Okay, suppose okay. In factor plot also there are many varieties actually. Let me, yeah, this is actually factor plot. By default, it is giving line chart. Okay, now let me produce box plot only. So what this will do is, this will produce box plot versus day versus total bill, but it will be grouped according to the time. It will be grouped according to time. Now you see this is a box plot. Kind equals to box means we are producing a box plot. But what we are generating, we are grouping it along time. So instead of time, let me generate gender. Then I think we'll get all gender. Where is gender? No gender. Sex. Okay. Because time it is not producing nicely. Now you see these are the box plot. Now the box plot were grouped according to the gender, male or female. Male this color, female this color. 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 Like this. Is it okay? So by default, what it was producing? It was producing line graph with errors. If you omit this kind, now you see what it is producing. It was producing line bars. This is lines. Actually, this is a line connecting average values, and this is the standard deviation. Now this is for different what? Different genders, male and female. Is it okay? It is simple. These are the average values. These are the errors. Errors. Errors means the deviation. Deviation from average value. So similarly, okay, let me post this one first. Let me write kind equals to box. Let me post this one. Let's give more tips from the graph. Okay, this is some how to infer. Okay. Let me draw this box plot. Now this is male, this is female, this is male, this is female. These are, you know, the box plot explanation. These are the average values. These are 75 percentile, 25 percentile, and you know, the outliers. All these things were there. Now I hope it will be clear how to infer from this box plot. Is it okay from box plot? Can you infer from box plot at least? These are the average values. Average tip. This is actually bill. Okay, you wanted to infer means give more tips from the graph. Okay, you wanted to infer from the graph. Is it right? No. Actually, this graph basically is between day and total bill. So if you wanted to play with tips, you give tips here. Who gives more tips? Where is this tips? Tip, not tip. Tip. Let me give tips. Now you can infer what do you want to infer from this data. You see here? Now, yeah, from this we can infer that average tip given by male is more on Thursday, whereas on Friday it was less. On Saturday also more. On Sunday it was less. That we can infer from this box plot. At least average values. Is it okay? From box plot we can infer this one, right? If you want to infer tips information. I hope it is clear.
So please post this code.
Yeah. This is X day. This is tip. How much tip they are given. This is grouping into male or female. If you change this grouping into something else, let us say smoker or non-smoker, you can give smoker. You give smoker. Yeah, that's all. Smoker. Then we are grouping into whether he is smoker or non-smoker. Yes or no? That's all. Let me paste this code. You change the parameters, then you can play with those things. X axis and Y axis. This is X data, this is X, Y, this is grouping based on this one. Based on the number of values. Here there are only 2 values, yes or no. Here there are 4 values, Sunday, Saturday, Thursday, something. This is family size. How many 2 people came here, 3 people came here, like this. 3 people like this. All this you can enter. So this is factor plot. So similarly, this Seaborn supports different other plots called joint plot. What is this joint plot? So joint plot means it combines 2 different plots. Okay. So that means what? Suppose you are generating X versus Y. You are generating some box plot or some line chart we are generating. So in order to, in addition to this line chart, you wanted to show how X looks like, how Y looks like. So joint plot means let me produce, then you will understand what is this joint plot. So let me produce a joint plot between total bill and tip. Okay. Or whatever you want. Total bill, total underscore bill. And let me generate and between tip. Okay. And I have to give what is the data. Data is tips. This is the data. Now you see what is this joint plot. So basically it was showing that this is the relation between X and Y. These are the values that were printed. Total bill versus tip. Now you see joint plot means here. This is the histogram of total bill. This is the histogram of tip. So that means we are getting many plots. We are joining histogram with the scatter plots. So scatter plot requires 2-dimensional data. Histogram requires 1-dimensional data. In the same figure, we are generating histogram for 1D data, tip and 1D data, total bill. Similarly, we are generating scatter plot for total bill versus tip. Okay, there is some other option here. There is an option, some other option, kind or something. You can change what we get here. Instead of scatter plot, suppose if you want some other plot, you can generate that plot here using some option. You can change these things also. Instead of histogram, if you want density plot, some other plot, you can generate. I think kind only, kind density. Let me give. I don't know whether kind. Okay, let me go back. Data, space, color, height. Kind is not there. Kind is there. Kind by default, kind is scatter. By default, kind is scatter. You can give these things: KDE, histogram, hex, all these things. So let me give kind equals to KDE. All these options, you can explore those options. KDE. So now you see what will happen. So this one will be hex density. This is also a density plot. So this is called contour plot. You please explore this contour plot. Here we are getting contour plot. Here we are getting density plots. Okay, this option. You can play with this option. So similarly, this Seaborn. So far what we are saying, this is a relation across 2 features, tip and total bill. So now this is tip histogram. This is what is this? This is total bill histogram. This is tip versus total bill. So instead of 2 features, if you want joint plots for 3 features, what you do? There is an option called pair plot. So for this pair plot, you simply pass data. That's all. What is the data? We have tips, right? So let me simply pass tips to this one. So it is an extension of generalization of joint plot. In joint plot, so let me give hist here. It will So if you give hist, what happens if you give hist? These are histograms. This is 1D histogram. This is 2D histogram, right? That's why it was showing like this. Yesterday we have seen 2D histogram means, right? If you want to give color map, all this you can give. So now you see, yeah, this is the generalization of joint plot. Joint plot is for only two features, total bill versus tip. Now, if you want to draw, so you see here, there are only three numerical values, total bill, tip and size. Others are text, right? So it will take, so we pass this tips data set. So therefore it will take only three features, total bill, tip and size. Now you see what the pair plot has generated. X-axis, this is total bill, tip and size. Y-axis, you see, this is size, tip and total bill. Now, by default, it is producing scatter plot. Now you can change this scatter plot to other plots also. Just now we have discussed, right? Now you see, whereas this one, this diagonal one, it is producing histogram. Why it is producing histogram? Because it is a single feature, total bill versus total bill. That's why it was producing histogram here. Similarly, histogram here. Similarly, histogram here also. So basically, pair plot is a generalization of joint plot. Is it okay? So far, any questions? Any questions? So we have covered many graphs.
Can we input the data from the Excel and can do the same things?
Yeah, that's what I answered, right? You can read data using pandas pd dot read underscore csv, then convert into data frame. The moment you convert into data frame, then you can do. This is the data frame. Basically, you see, this is a data frame. That's why I've shown you this one. Read your data set from Excel, convert into data frame. Rest of the procedure is same. We are passing this data frame. That's all, right? You pass your data frame.
Okay, sir.
So let me, otherwise, if I have some Excel, let me import Excel. I think the command is pd underscore csv file. Okay, if I have csv file, I don't know whether I have or not. Example, Excel, but is it worksheet? This is worksheet. XLS also, I think it will work. Excel sheet, the command, I forgot the Excel sheet command, but CSV, you can simply read underscore CSV. Excel, the command is read underscore. Okay, let me first write whether it will come or not. We will see. Since you are asking, import pandas as PD. So PD dot read. Oh, it is not coming. Read underscore. Yeah, read underscore CSV. Yeah, read underscore Excel. Can you see? Read underscore HTML, read underscore JSON. Right? Simply call this command. Okay, let me read underscore Excel if you want. Excel. Let me give. Okay. Now, first of all, since I am in Google Colab, if you want to import some file here, there are two commands. If you want, so you see, files will be here. If you simply say X, okay, let me import first. So what is that command from Google Colab? Import files. Okay. Then files dot upload. You call this function files dot upload or uploaded. Okay, let me see files dot whether it will come or not. I'll see. Files dot uploaded. Let me call some error is there. It will show us files dot upload only. Right? Yeah. Someone posted Rohan. Files dot upload. and let me store it somewhere. Now, first let me run this command. Let me run this command first. Now it will ask you to choose choose the file from local folder, local directory. Let me choose from download.
Please tell for Jupyter Notebook also.
Jupyter Notebook you can directly read if it is in your local folder. No need of doing this one. Where is that file? IT2. What is this IT? Okay, I should not use this one. Okay, let's say list of registered students registered for MAD. No. Okay, this one let me import. Okay, I have imported this one. Okay, now let me. You see, after importing, you see where this file is there. This file came here. What is this? This is Excel file only, I think. This is Excel SX. Okay. Now let me read this file. How? Give simply the name. Online. You can give the name of the file here directly. What is the name of the file? .xlx. Invalid syntax. As okay. Can you see? It was by default it was importing into data frame. Excel underscore df. Now let me same thing. No need of storing also. You can store also. Is it okay, Venkat? Some Venkat also asked. Someone else also asked. See? Yeah, in Jupyter you have to add the path if it is somewhere else. If it is in your local directory, means in the same directory, you can directly give. Yes, for Jupyter you have to give entire path. Whereas in if it is in the same folder, then you can directly give. Now you see it was imported into data frame. Can you see? Because these fields, these rows was not there. That's why it was giving by default none. Now you can play with this data frame. Now we have uploaded these things. See, now you can play with this one. Is it okay? Venkat and someone else also asked. Yes, okay. Venkat, someone else also asked. I don't know who posted. Okay, someone.
Sir, I have imported the file, but I'm not able to read it. I'm using Jupyter Notebook.
You have imported.
Yes, sir.
You are not able to. Okay, Karthik also asked. Imported, but you are not able to read means what? This read Excel. This you
Yes,
have
sir.
given.
Yes,
This
sir.
path,
Yes, sir.
this path you have given.
Yes, sir.
So here you are getting error.
Yes, sir.
So for Jupyter, these things are not required. You have to pass the path of the file. You please check once again. See, these two commands are enough for Jupyter. Simply import pandas pd dot read Excel. If you have CSV file, read underscore CSV, read underscore CSV. JSON file, read underscore JSON. All this is simple. It will directly it is exporting also. It is importing into data frame directly. No need of writing other commands also. Can you please check once again your code? This is enough actually. How to read? Yeah, some question. How to read infer the total bill versus total bill histogram. Okay, total bill versus total bill. Dharmendra, actually, since it is the same data means what? You see, basically the idea of this pair plots or joint plot is to what? Is to analyze the relation between two different features, right? Now What is the relation between total bill and total bill? Is there any relation? Can you say? That's why by default, what it is giving is, it is giving histogram. Histogram means what? Number of what? Okay, this is total bill, right? So you see, number of people who have given, whose bill is 20, whose total bill is 20. This one. Okay, that one you're asking. Okay, let me, yeah, okay, let me, so this is total bill. This is also 40/50. This is also 40/50. So what he was asking is how to infer this one. What this histogram basically represent, right? So yeah, the total bill value, you see here, first we'll see here, total bill value 20. Here this is 20, right? Total bill value 20. How many are there? More than 10 are there. 10 are 12 are there. 12 people are there. Total bill value 23. This is after 20, right? This line is 20. So let us say total bill value 25. How many are there? 10 are there. Total bill value 20 something like this. Is it okay? That's how we infer. Dharmendra, is it okay? Right? This is x-axis. It will say total bill value 20. This will say how many people are there. Frequency. Histogram means frequency, basically. That's all. Out of these 244 people, these many people have total bill value 10 like this. So this also you can change instead of histogram. If you want density plot, all this you can play. So you can play with all these things. So I hope it is already 6:30. So I thought of covering SymPy also. SciPy and SymPy tomorrow I will cover. Yeah. SymPy very few topics I will cover. So basically let me give a brief introduction to SymPy. So basically the SymPy is a library for symbolic mathematics. That's why it is known as SymPy, symbolic Python library. So basically many people from science and engineering, they wanted to work with exact values rather than approximate values. Then they can go for this SymPy library. What is this exact value and approximate value? So let me give you an example. Let me delete this one. So suppose you wanted to find square root of some number. Okay, let me import math. Math supports the square root. Okay, math that square root of 9. What is the value? 9. Okay, it is all right. It is producing. But let me give 8 to this function square root. What it is producing? It is producing 2.824842 something. But is it an exact value? Is it an exact value? No, it is not an exact value. It was approximated to some number of points. What is the exact value of this 8? How to find exact value of this 8? So this SymPy, you can import SymPy like this, SymPy. Now call SymPy.square root. What is the exact value you will know. So it will not give some approximate values. It will give exact values. So what do you mean by exact value of square root of 8? See now. Why it is rotating for this much time. Has not executed or what? Yeah, you see 2 root 2. Do you agree that 2 root 2 is the exact value of square root 8? 2.82 is not an exact value of square root of 8. So basically the SymPy basically deals with exact values rather than approximate values. This is the one thing about SymPy. The other thing is you can define symbols. Using symbols, suppose you wanted to write an expression ax square plus by cube plus cx square something plus cx cube cx like this. You wanted to write expressions. How to write these expressions? You can write using SymPy. And for this expression, you wanted to find derivative with respect to x, derivative with respect to y, integration with respect to x, all this symbolically, not numerically. You have some complex expressions. You wanted to find derivative of that complex expression. You can do with pen and paper, but it will take so much of time. But using this symbolic library, this SymPy library, you create that expression first, give it to some symbolic variable. Then you can find derivative of that using a single command. You can find integration using a single command. All this you can do with this symbolic Python library. I hope the idea of symbolic Python is clear. I may not spend much time. I will introduce all these things, basic things, differentiation, integration, limits, how to calculate limit of a expression using this symbolic library. Is it okay? Suppose you have some big expression, 3x cube plus 6x plus 2. You wanted to divide into factors. You can divide that expression, complex expression, into factors using the symbolic Python library. Is it okay? Similarly, you have some product of expressions, x plus 1 plus x plus 2 plus x plus 3 plus x plus 4 plus x plus 5. You wanted to find a single expression for all these factors. You can find this using SymPy. It supports many other functions. I am describing few functions here. So since it was already 6:30, I will stop here. So tomorrow I will finish this SymPy and SciPy. So the next session on machine learning starts at 6:40. Please come back by 6:40. All are requested to come back by 6:40. So let me directly post it in group. Okay, I'm stopping the sharing. If you have any questions, you can ask me. Otherwise, I conclude this session. But please join by 6:40 sharp. Actually, in the beginning, I forgot to record. So I hope you understand this issue of.
Start record. So in the previous session, we have discussed what is machine learning, what are the different types of machine learning. Then we have started discussing supervised learning. In the supervised learning, there are two main types of problems: regression problem and classification problem. We started discussing regression problem. Then one of the solution also we have discussed, linear regression solution. And we have also implemented that linear regression using scikit-learn library, right? So the next, another solution for the regression problem is polynomial regression. So in case of linear regression model, the output is modeled as a linear combination of the input variables, linear function of the input variables. So what if the data is non-linear in nature? Suppose if you cannot fit it, the straight line is not well fit to the data, right? So what if there is a data with a non-linear nature? So then we go for polynomial regression. So here the output is modeled as a non-linear function of the input variables. Like as you can see in the figure or in the hypothesis specified there as an equation, hypothesis is equivalent to theta naught plus theta 1x plus theta 2x square plus theta 3x power 3 so on theta m x power n. So whereas if you take the linear regression, what was the hypothesis in case of linear regression? In case of linear regression, the hypothesis or the model is theta naught plus theta 1x. We call it as a first order polynomial, or it is just a line equation. Right. So whereas if you see the polynomial regression, we have the additional variables here, x square, x cube, x power m, so on. So here the output is modeled as a nonlinear function of the input variables. So if you take m equal to 2, then you get the second order polynomial, and the equation looks something like this: theta naught plus theta 1x plus theta 2x square. And this is how the curve looks like, the model looks like, the blue one, the blue curve, right? The problem with this second order polynomial for this particular case is So here the curve comes something like this, right? It means that the size of the house increases after some time, after some point of time, then the price is decreasing. So it's not a good model for this. If you go for the third order polynomial, then the equation is this. The curve looks something like this green curve. Okay, maybe it is better than second order polynomial, right? In any case, so this is how you can model hypothesis as a nonlinear function of the input variables in case of the polynomial regression. So now the question is, given this data, a friend has a house of 750 square feet, how much can they be expected to get? Suppose if you fit a second order polynomial to the data and the curve looks something like this, the model looks something like this, isn't it? So with this, 750 means it is somewhere around $200,000. Okay, so essentially, if you see here, what are we doing here? Sorry. So what are we doing here? Given X, which means the size of the house, we are generating X square, X power 3, X power 4, and so on, based on the degree of the polynomial, isn't it? So this is X is the original features. You are generating the additional features. Additional features are X square, X cube, X power 4, so on. Right. So suppose if I map this X square to like X2, X1, X square to X2. If I say X2 is equivalent to X square, X cube is X3, X power 4 is X4. Right. Suppose if I do this, so I can rewrite this equation as, let's say that I have 4 features. So I can rewrite this equation as theta naught plus theta 1 x1 plus theta 2 x2 plus theta 3 x3, so on. Isn't it? So isn't it looking like a linear regression? Linear regression model, which we have seen in the previous class, right? So the only additional thing, what we are doing here is the generation of the new features, right? X square, X cube, and X power 4, and so on, right? And this is with one input variable. Let's suppose if you have multiple input variables, let me write it here. Let's suppose instead of X, you have X1 and X2. So how do you generate second degree polynomial features? You will have to generate x1 square, you will have to generate x2 square, and also x1 and x2. Sorry, x1 times x2. So if you go for the third order polynomial, then you will have to generate x1 cube, x2 cube, x1 square, x2, x1, x2 square, and so on. So if you go for the fourth order polynomial, then x1 power 4, x2 power 4, x1 cube, x2, x1, x2 cube, x1 square, x2 square. So all these are the different features that you need to generate with a multiple, right? Suppose if you have 3 features, x1, x2, x3, then in that case, for the second order polynomial, you will have to generate x1 square, x2 square, x1, x2, x1, x3, x2, x3, and so on. Right. So this is how you can generate when you have a multiple input variables. If you go for the mth degree of the polynomial. Right. So once you generate the features, it is just like applying linear regression on that model. So it's same as that. Right. So let us try to understand this. Is my voice clear? Is my voice clear? Following me? Okay. Okay. Thanks. Thanks. Right. So let us try to understand this polynomial regression a bit more. So for that, I have generated a data using sine 2 pi x, right? So my input variable is x that I have randomly generated number in between 0 and 1, and the output variable is sine 2 pi x. It means that this green curve is the underlying model from which I have generated this data, and I have added some random noise to that generated points. So these blue points are the points that I have randomly generated using sine 2 pi x curve, right? So the sine 2 pi x is the underlying model from which I have generated the data, the green curve, and the blue points are the points that I have generated. 10 points I have generated. And the hypothesis is this: theta naught plus theta 1 x plus theta 2 x squared plus so on theta m x power m. So here, what m should we choose is determined by the model selection, and given m, what thetas we should choose is determined by the parameter selection. So these two things are different. Model selection is different from the parameter selection. So what m we choose, that determines the model, and given m, what theta should we choose is determined by parameter selection. So these two things are different, right? So now, so this is the data that I have at hand. Now let us try for different values of m. So when m equal to 0, so if you see this model, if I substitute m equal to 0, what would be the hypothesis? My hypothesis is just theta naught, isn't it? So when m equal to 0 and when m equal to 1, hypothesis is theta naught plus theta 1 x. And when m equal to 2, this would be theta naught plus theta 1 x plus theta 2 x squared, and so on. So let's try to see, let's try for the different values of m and see what is happening, right? So if I see, this is the original data set and the green curve is the underlying model from which I have generated the data. So ideally, I have to learn a model which is close to the underlying model, isn't it? We are interested in learning a model which is close to the underlying model, right? So let's try m equal to 0, which means 0th order polynomial, and this is how the predicted model looks like. So this is how the model that we have learned, the red curve, and this is the underlying model, the green curve. So do you think it is close to the underlying model? Is it representing the underlying model? The red line is not representing, right? It's not a good fit to the model, isn't it? So it's not a good fit to the model. So let us try higher order polynomials. Let's try first order polynomial. First order polynomial means your hypothesis is theta naught plus theta 1 x. And this is how it is looking like. So it is trying to fit a line to the data. So first order polynomial is essentially a linear regression, right? So when you fit a linear regression, it tries to fit a line to the data. So I'll ask you two questions. The first one is it better than the previous model or not? Is it better than the zeroth order polynomial? Yes, it is better than the zeroth order polynomial. Do you think it is a good fit to the data? Do you think it is representing the underlying model? No, it's not representing, right? So let us go for the higher order polynomials. Let's try third order polynomial. So when I try third order polynomial, this is how it is looking like. So again, two questions. Yeah, it is better than the previous two models, and it is also closer to the underlying model. I hope all of you would agree with me, isn't it? It's not perfectly giving you the underlying model, but it is close to the underlying model. Let's try to improve further, and let's try the higher order polynomials. So let's try. So if the order of the polynomial is increasing, my model is improving, right? So let me try the ninth order polynomial. So if I try the ninth order polynomial, wow, I have got very beautiful curve, isn't it? It is going through each and every training point. It means that it is perfectly fitting to the training data. It is perfectly fitting to the training data. But do you think it is representing the underlying model? Given any new point that is generated from the same distribution, do you think it will predict it correctly? No, isn't it? So it will not predict it correctly. So what is happening here? Somebody said it is overfitting to the data. So what is overfitting to the data? Overfitting means a situation where it works very well for the training data, But given new instances, it will not be able to generalize that to the new instances. So it will not be able to predict correctly for the new instances. The test error would be very high, training error would be very low. So this situation we call it as overfitting. So what is the problem here? What is the problem here? Why is it oscillating too much in between the data points? Because in a process of fitting exactly to the training data points, you are not keeping any control on the parameters. So let us observe what is happening internally in terms of the parameters or the weights. Right. So if you observe parameters, so do not confuse between W and theta. So W0 to W9 here are in our notations theta naught to theta 9. Right. So let us try to see the parameters of a model. That means theta naught, theta 1, theta 2 and so on. Right. So when I'm equal to 0, we only have theta naught which is 0.19 which is in the smaller range. When I'm equal to 1, we have two parameters theta naught and theta 1 and that is also in the smaller range. When m equal to 3, we have 4 parameters. They are also relatively in the smaller range. But if you see when m equal to 9, we have 10 parameters and there is a huge range difference between the parameters and they are in very bigger range, isn't it? So it means what? When you are trying to fit exactly to the training data, you are not keeping any control on the parameters that you are learning. So with that process, what is happening? The lot of variance is induced into the models between the parameters. So there is a lot of variance is coming between the parameters and that is inducing a lot of variance in the model. So as a result, the model is overfitting to the data. So what is the root cause for all of these problems? All these problems? The root cause is that you're not keeping any control on the parameters. You're allowing them to grow as big as they grow. So as a result, lot of variance is induced into the model. Right. So what is the solution? The ideal solution is we should penalize the high weights that contribute to high variance and sensitivity to the outliers. Isn't it? Correct? Right. So the ideal solution is to penalize the high weights that contribute high variance and sensitivity to the outliers. So what is the earlier objective? In case of linear regression, the earlier our objective is to minimize the difference between the actual and predicted over all the training instances, which means this. So this is predicted, this is actual. And we want to minimize the difference between them for all the training instances I equal to 1 to m. So this was our objective in case of linear regression. But now what is the problem? Problem is that if you just focus on that, if you don't keep any control on the weights, then it will induce lot of variance into the model and therefore it is overfitting to the data. So for that reason, we are saying that the solution is we should penalize high weights that contribute to high variance. So that is the reason why we are adding theta to the objective function. Because we want to minimize this, we also want to minimize this. So this lambda is some weight that you give to this objective, the sub-objective of this loss function. Right. So are you with me? Any queries so far? Are you with me? Following it? Right. Good. So let us proceed. So this is what we call it as a regularization. So we are calling a regularization term to avoid overfitting. So this we call L norm. Okay, when L equal to 1, we call it as L1 norm. When L equal to 2, we call it as L2 norm. And depending on what kind of regularization that you select, we have different kinds of regressions. Suppose if you take L1 norm, when L equal to 1, I said it is L1 norm, then we call it as a lesser regression. If we take L2 norm, we call it as a ridge regression. Right. So L1 norm can be written as absolute values of theta 1 plus absolute value of theta 2 plus absolute value of theta 3 plus so on. And that's how you can express this quantity. Right. And this is how it can be visualized. So according to this objective earlier, our objective is to reach to this point where j is minimum. So this is the point where g is minimum. So we want to learn, let's say this is theta 1 and this is theta 2. So we want to learn theta 1 and theta 2 such that we reach to this point. We want to learn this theta 1 and this theta 2. Right. But now, according to this new objective, I want to minimize this also, theta also, which means this is the point I want to reach according to this objective. According to this objective, I want to reach to this point. Right. So there is a difference of opinion between these two objects. So what is the solution? We have to learn a point where these two of them agree. Right, which means this intersecting point I'm interested to learn. Right, so this is a point that I am interested to learn. Right, and similarly, ridge regression uses L2 norm. L2 norm means square root of theta 1 square plus theta 2 square plus so on. Right, and according to this objective, L2 according to L2 norm, I'm interested to go here. According to this, I'm interested to go here. Right, so I'm interested to learn the intersecting point according to this new object. Right, and elastic ridge regression, elastic net regression uses both L1 and L2 norm with some proportion, lambda 1 and lambda 2 appropriate weights. And the curve for them can be visualized as in between the diamond and the square, that green color one that you can see there. Right. So we'll implement this polynomial regression, lesser regression, ridge regression, and elastic net regression. And then we'll go to the classification problem. Right. So there is a question here. Question from Sion Kumari okay. So how to decide which norm we should consider? Okay. This is again depends on you can use any of these norms. It's not a problem, but each one of them has certain properties, and based on our requirement, we have to consider using one of these norms. So the general, if it is a general requirement of overfitting, then you can use any of the norms. There are some additional properties of these regularization terms. So if you are interested in applying those properties, individually you have to go for that. For example, I'll tell you one of the property. So like for example, if you see the L1 norm. Okay. So if you see the L1 norm here, if you see the intersecting point, can you tell me what is the value of theta 1 at this point here? What is the value of theta 1? Theta 1 value is 0, isn't it? 0, isn't it? So what is your model? Your model is theta naught plus theta 1 x1 plus theta 2 x2, so on, right? So when theta 1 equal to 0, what weightage that you are giving to x1? What is the weightage that you are giving to x1? You're not giving any weightage to x1, isn't it? Zero weightage, isn't it? So you're not considering the feature x1 at all, isn't it? It means what? This process is automatically selecting the important features, isn't it? Ignoring the unimportant features, isn't it? It is only considering the features that are important for the prediction. Okay, so this has an additional property of ignoring the unimportant features or the redundant features. So if you are interested in simultaneously reducing the dimensionality of the data set, if you want to only select the features, but not interested to select, you're not interested to select the unimportant features. You are only interested to select the important features, right? And if you want to reduce the dimensionality, right? If you want to reduce the computational, if you want to improve the computational speed, then it is better to go for the lossy regression. Alright, so this is the additional property that it has. So similarly, each one of these regression techniques has some additional properties. So based on that and your requirements, you can choose one of them. But if the general requirement is just O, if you want to just avoid the overfitting, any of them works fine. Right. All right. So let us finish the classification also. So at a time we'll go to the implementation part. Is that fine? Shall I proceed? All right. So let us finish the classification part also, and then we'll move to the classification. And there is one more concept, ensemble learning techniques. Let us finish both of them, and we'll go to the implementation at a time. So what is classification task? It is also a supervised learning problem. So therefore, we have given a triangle set of pairs x1, y2, x2, x1, y1, x2, y2, so on, xm, yn, where xi is the feature vector and yi is a discrete target variable. Okay, so here the target variable is discrete, not continuous. So in case of regression, the target value is continuous, but here the target value is discrete. So the task is to predict for the new instance. So given a new instance, should be able to predict. For the new instance, we only know the features, but we do not know what is the target variable. Right. So there are different kinds of classification techniques, and each one of them try to discriminate one class with the other class in certain way. Okay, like for example, if you take the nearest neighbors, the decision boundary could look something like this, as you can see in the figure, right? So there is a kind of discrimination, one kind of discrimination, and this is non-linear in nature. And if you see the decision trees, the discrimination is different based on the features that it individually it checks one by one, and based on that it discriminates. And if you see the linear functions, the discrimination is different. It tries to separate one class with the other class using a line or a hyperplane. If you see the nonlinear functions, the decision boundary could be different from the other classifiers. So the point here is that each one of these classifiers learn the decision boundary in certain way. Okay, so based on that, how they learn the decision boundaries, we have different kinds of classifiers. So let's see some of these classifiers one by one. Okay, so we have seen linear regression, right, where we have a line that fit to the data, right? So similarly, in case of logistic regression, also we have a line that separates the data, not just fit to the data; it separates the data. So it is a probabilistic approach to learn a classifier. It means it is learns the uh, probability that new instance belongs to a certain class, right? So here, so if you see the linear regression model, what is the hypothesis? Hypothesis is a line theta naught plus theta 1 x in case of linear regression. So that's what the hypothesis is. It's theta of x equivalent to theta naught plus theta 1 x, right? But here in case of logistic regression, because it is a class, it solves the classification problem. It gives the hypothesis as probability that output belongs to class 1 given x and theta. Right. So if I know that what is the probability of y equal to 1, can I guess what is the probability that y equal to 0? Let's assume that we have only two classes, 0 and 1. And the logistic regression is for binary classification problem. Okay. So now the question to you is, if I know what is the probability that y equal to 1, can I guess what is the probability that y equivalent to 0? So what is the probability that y equal to 0? This is equivalent to 1 minus probability that y equivalent to 1 given x and theta, isn't it? Because we know that probability of y equivalent to 1 plus probability of y equivalent to 0 is 1. Probability of an event plus probability of its negation equivalent to 1, isn't it? So if I know what is the probability of y equivalent to 1, I can easily guess what is the probability that y equivalent to 0, isn't it? So this is what it gives. So h theta of x is the sigmoid of theta transpose x. Your theta transpose x is a linear function. Theta naught plus theta 1x is theta 2x2 and so on. Right. So this line is converted into a probability. So here also we have a line, but line is converted to a probability by giving it to the sigmoid function. Right. So imagine that we have a line which separates the positive class from the negative class. I mean the instances from the positive class with the instances from the negative class. So let's suppose I have a points, all positive points one side and all negative points another side. So if you imagine there is a line. Right. So when you predict a new instance, if that is on the line, if the new instance is on the line, it means that probability that it belongs to certain class, probability that it belongs to a positive class is 0.1, 0.5, right? Which is exactly in the middle, isn't it? So probability that it belongs to class 1, let's say it is class 1, it is class 0. Okay, is 0.5, isn't it? So if it is the positive side of the plane, then the probability that it belongs to class 1 is greater than 0.5, isn't it? So if it is this side of the plane, then the probability that it belongs to class 1 is less than 0.5, isn't it? So that is how this function works. So theta transpose x, z of theta transpose x, when z of z is equivalent to 1 by 1 plus e power minus z. Let's suppose if theta transpose x is equivalent to 0, which means the point is lying on the plane, isn't it? So when theta transpose x equivalent to 0, what is z of z? Z equivalent to theta transpose x. When z equivalent to 0, what is this value z of z? What would you get when z equal to 0? Z of z, when z equal to 0, what is the value of z of z? That is equivalent to 1. 1 by 1 plus e power 0, and this is equivalent to 1. So therefore this is equivalent to 1 by 2, and this is 0.5. So what did you say? I didn't put it. It's not 1 ma'am, Diksha ma'am. It is 1 by 2. Isn't it? Right. So it is 1 by 2, that is equivalent to 0.5. Okay. So when theta transpose equivalent to 0, it means when the point is lying on the plane, you are not sure whether it belongs to the positive class or the negative class. Isn't it? Because it is exactly in the middle. Right. So let's say when theta transpose x is a big positive number. When theta transpose x is a big positive number, it means when z is a big positive number, then what is the value of z of z? Z of z is 1 by 1 plus e power minus some big positive number. Okay, so e value is 2.71, right? 2.71 power minus of a big positive number. It means this is almost close to 0, nearly equal to 0. So therefore, 1 by 1 plus 0, and this is close to 1. Isn't it? So when z is a big positive number, what is the probability that you're getting? Probability that you're getting is close to 1. It means when the point is far away from this line, you're more confident that it belongs to positive class. The point is more away from this plane, and if it is on the positive side of the plane, then you are more sure that this point belongs to class 1. Right? Following me? Or you bored with this mathematics? I can skip this if you want. I just want to explain this, what is working. Okay. Right. Right. So when this z, it means theta transpose x, is a big negative number. So then you substitute a big negative number in this equation, this would be equivalent to 1 by 1 plus e power minus of minus big negative number. Means this thing is close to infinity. 1 by 1 plus infinity. This is equivalent to 1 by infinity, and that is equivalent to 0, close to 0. Okay. So when probability of y equivalent to 1 is close to 0, then what is the probability that y equivalent to 0? It should be close to 1, isn't it? It means what? When this theta transpose x is a big negative number, you are predicting that as a class 0, isn't it? So it means graphically, if you want to visualize, if it is a if the point is on the negative side of the plane and it is far away from this line, then you are more confident that it is a negative number. I mean, a negative class. It belongs to negative class, right? So this is how the logistic regression works. It is converting this prediction to a probability. If it is one side of the plane, then it is giving positive side of the plane, then it is giving high probability that it belongs to class 1. If it is on the negative side of the plane, it is giving high probability for a negative class. So then how would you classify? If the outcome is greater than or equal to 0.5, then you will classify it as class 1. If the outcome is less than 0.5, then you will classify it as so here there is a question from Diksha ma'am. Why we are taking transpose of the theta? Okay, good question. I'll explain you, ma'am. So let me find some space for this. Okay. So here, if you see the model, that linear model, which is theta naught x naught, where plus theta 1 x1 plus theta 2 x2, so on, isn't it, madam? So in which x naught equivalent to 1, right? So let's suppose when you go for the vectorized representation of this or vectorized implementation of this, suppose if you represent this theta values as one vector, theta is equivalent to theta naught, theta 1, so on, theta m, let's say theta n, theta d dimensions. Okay. Similarly, you can represent x as also x naught, x1, x2, so on. Okay, for multiple instances, you can have another x, another x, another x, like that. Sorry, like this. X naught, x1, so on, x d. Like you can have multiple instances. Right. So if you multiply theta transpose with x, what would you get? What would you get, man? What is theta transpose? Theta transpose is theta naught, theta 1, so on, theta d. And what is x? X is x naught, x1, so on, c. Okay, so when you multiply both of them, what would you get? Theta naught, x naught, plus theta 1, x1, plus so on, theta d, x d. Okay, so to get this model, we multiply theta with x and we assume that theta is a column vector. That is why we are taking transpose of this. Okay, it's all based on your assumption. If you assume it to be just a row vector, then you can just multiply theta with x. If you assume it to be a column vector, then you have to take theta transpose with x. Okay, it is here. I have already unnecessarily written all this. I didn't realize. So theta transpose x is this. X is this, and theta is transposes. Is that clear, ma'am? Diksha, ma'am? Is that clear? Yeah, theta is always a vector, either row vector or column vector. Here the mission is that it is a column vector. Right. So that's what the logistic regression model. It learns the probability that y is equivalent to 1. Right. So if it is just the positive side of the plane, but just if it is close to the plane, then the probability may be around some 0.6, something like that. So the point is more far away from the line, it means that you are more confident that it belongs to one of the classes. So if it is a positive side and if it is far away from the line, then you're more confident that it belongs to class 1. If it is a negative side, but it is far away from the line, then you are more confident that it belongs to class 1. Okay. So if it is somewhere around the line, but strictly falling on one of the sides, then you're classifying as the one of these classes with high probability, but you're not that confident. It means your probability is close to 0.5. Right. Right. Any doubts about this so far? So this is the logistic regression objective. So what is the objective of linear regression? Anyone quickly? Logistic linear regression objective. We want to minimize the difference between the actual and the predicted, isn't it? H theta of x minus y whole square. We want to minimize this, isn't it? Right. Here also we have got a different objective. We cannot take simply squared loss here because with this hypothesis, squared loss will result in a non-convex optimization. Okay. So, but the intuition behind the logistic regression objective is also same as the intuition behind the linear regression problem, linear regression objective. So, what is the intuition behind any of these loss functions? Intuition is if the predicted and the actual values are same, then your loss should be 0. If the actual and the predicted values are different, then we should penalize the loss with some high value, isn't it? Isn't it? Right. So that is the intuition behind any of these loss functions. So let us see whether that is happening or not with this loss function. Right. So I can rewrite this loss function as this, right? Because y takes one of these values, 0 or 1, because it is a binary classification problem, right? So yi target value is yi can take any of these two values, 0 or 1. So when yi equivalent to 1, substitute yi equivalent to 1 in this equation. So when I substitute yi equivalent to 1, this part becomes 0 because 1 minus yi is 0 and 0 multiplied by anything is 0. So this whole part is 0, right? And here yi equivalent to 1. So I just get minus log h theta of xi, right? Similarly, when yi equivalent to 0, this part becomes 0 and this is 1. So the resultant would be minus log 1 minus h theta of xi. Okay, so now one question to you. If y equal to 1 and h theta of x equivalent to 1, y equivalent to 1 and h theta of x equivalent to 1, is the prediction correct or wrong? Y equivalent to 1, h theta of x equivalent to 1. Y is the actual value, h theta of x is the probability that it belongs to class 1. Is the prediction wrong or correct? Simple question. Anyone quickly? The prediction is correct. So then what would be the loss when the prediction is correct? What should be the loss? The loss should be 0, isn't it? So when h theta of x equivalent to 1, here, what is the log 1 value if you see? This is the plot of log. Log 1 value is 0. It means you are adding a 0 penalty to the cost function. Right? So when y equivalent to 1 and h theta of x equivalent to 0, sorry, when y equivalent to 0 and h theta of x equivalent to 0. So that is also another correct case for the prediction, right? Y equal to 0, h theta of x equivalent to 0. The prediction is correct. So in that case also you should add a 0 penalty to the cost function, isn't it? When y equal to 0 and this becomes minus log 1 and log 1 is 0, therefore you are adding 0 penalty to the cost function. Let's say a different case. Y equivalent to 1 and h theta of x equivalent to 0.1. Let's say y equivalent to 1, h theta of x equivalent to 0.1. So the prediction wrong or correct? H theta of x equivalent to 0.1 means the probability that it belongs to class 0 is 0.9. There is a higher chance that it belongs to class 0. So therefore, the prediction is wrong. So in that case, you should penalize the cost function. So when it is 0.1, it means somewhere around here, log value is somewhere around minus 1.5. Minus 1.5 minus of minus 1.5 is 1.5. It means you are penalizing this cost with some positive number. So similar is the case with this also. Right. So that is the intuition behind the logistic regression cost function. Right. So just to recall, logistic regression is a probabilistic approach to learn a classifier. It gives the hypothesis is the probability that y equivalent to 1. Right. So, and this is the cost function to learn that. There is a question here. Vrinda, based on the high loss, the penalty value increases. Yes, ma'am. Based on the high loss means the more it is deviating from the original, actual value, then the more loss you will add to the more penalty you will add to the loss function. If it is less deviating, then you will add less penalty to the cost function or loss function. Yeah. So that's all about the logistic regression, and this is for binary classification problem. You can easily extend it to multi-class classification problem. So the next one is support vector missions, right? So in case of support vector missions also, it is trying to learn a line or a hyperplane that separates one class with the other class. But the only difference here is that it tries to learn a line that maximizes the margin. Okay, so I'll ask you a very simple question here. Suppose we have given some two groups of houses, right? So one is this group, this is a set of houses, and another is this group, another set of houses. So suppose you are an engineer and somebody asks you to lay a road in between these two group of houses. Okay, so how do you lay a road? Would you prefer this kind of road or would you prefer this kind of road? Let's say this is road 1 and this is road 2. Which one would you prefer? Road 2 will prefer, isn't it? Why? Because the margin is maximum in case of road 2, isn't it? So you will get a better width road in between these two groups of houses, isn't it? So the point here is that if you have a maximum margin classifier, then what would happen is that, yeah, evenly distributed. This is far away from both of the groups. So when the new instance comes, which is from the same distribution, there is a high chance that it is close to this. Suppose if the data is generated from this distribution, there is a chance that it is close to this. Suppose if the data is generated from this group, then there is a chance that it is close to this. So when you separate this two groups with a larger margin, even if it generates from this from the same distribution, then there is a higher chance that it correctly classifies because there is a larger margin between these two groups, right? So that is the intuition behind selecting the larger margin classifier. Right. So margin, you can define it as the width of this classifier before hitting the data points of the either class. Right. And the points that hit, it means the border of this margin, we call them as the support vectors. Right. And we are interested in learning a line with a maximum margin, line or a hyperplane with a maximum margin in case of support vector missions. And this works for only linear data. The basic linear SVM works for only linear data. That means if there is a line, I mean, if you can draw a line that separates one class with the other class, then that is linearly separable data. Right. So this is an example of linearly separable data. The one that you can see in the first figure. There are green points that belongs to one class and there are white points that belongs to another class, negative class. Right. So you can clearly draw a line between these two classes, isn't it? So then we call it as the data is linearly separable. Okay. So when the data is linearly separable, linear SVM works. Right. And you are interested in learning a line or a hyperplane that maximizes the margin. So what if data is not linearly separable, like the one you can see in the figure? So do you think it is a linearly separable data, this one or this one? Can you draw a single line that separate one class with the other class? Red versus blue or red versus green. Can you draw a line that separate one line that separate red with green or red with blue? You cannot draw a single line, isn't it? Line or a hyperplane that separate with one class, separate one class with the other class, isn't it? Can you draw a line? Can you draw a line that separate one class with other class? We cannot draw a line. So therefore, the data is not linearly separable, right? So what is the solution? If the data is not linearly separable, the solution is that we transform the data into another space where the data is linearly separable. Okay, so like if you see the two-dimensional data is transformed to a three-dimensional data, right? And your if you see this the three-dimensional space, the data is linearly separable. You can draw a hyperplane that separate one class with the other class. So when you add a new dimension to it, the problem is becoming easy. So if you see the problem from a different angle, the problem becomes easy, isn't it? So this happens with many of our real life problems also. So we sometimes think that we have no way out, but when you see the problem from a different angle, the problem becomes so easy. So you may think that is this the problem that I worried about so much, isn't it? So when you see the problem from a different angle, the problem is becoming so easy. So the same thing applies here also, that when you are adding a new dimension and you're bringing it to a space where so okay, my voice is low. Okay, let me. Yeah, I'll. So is my voice clear now? I think my voice is straight. I think. Okay. So yeah. So let me try to speak loud. So there's a question from Naman Agarwal. Real world. Okay, real world. You mean to say that some real world data sets? Do we plot our input data and then decide which classification we have to use? Actually, it may not be possible always because the number of dimensions may be very high that you may not be able to plot them. Right. So in general, we try with the different kernels and see which is working better. But the kernel works for the linear data also. Right. So that way, if you have some domain knowledge, you can judge which kernel to apply. Otherwise, you can try with the different kernels and see which is working well. Right. So now, similarly, if you see this problem, if you see it in a one-dimensional space, this is not linearly separable. Right. But if you add another dimension, which is x square, so now you represent the data with x and x square in two-dimensional space. Right. So this is how it looks like. When you represent this data in a two-dimensional space, this is how it is looking like. So you can see that you can draw a line which separates green point from the red points in two-dimensional space. So the data become linear in two-dimensional space. So the data is linearly separable in two-dimensional space, and the model that you're learning is linear in nature in two-dimensional space. But when you bring it down to the one-dimensional space, the model is non-linear. This is how it is looking like. Okay, so see the beauty of it. So the linear in the new representation is equivalent to non-linear in the old representation. If you see the one-dimensional space, the data is non-linear. If you go for the two-dimensional space, the data is linearly separable. Therefore, you're learning a linear separator. But when you bring this down to the one-dimensional space, you are actually learning a non-linear model. Right? And SVM is also a two-class classification problem, and there are many approaches for handling multiple classes. You can extend this binary SVM to multi-class SVM. So you can combine multiple binary classifiers to solve for multi-class classification problem. One against all, one against one, decision tree structure, binary tree structure, error correcting codes are the different ways that you can extend binary classification, binary SVMs to multi-class SVM. I'll explain quickly one or two of these extensions. So the idea here is combine multiple binary classifiers to solve for the multi-class classification problem. Right? Suppose I have three classes. It is a multi-class problem, right? More than two classes is a multi-class classification problem. So one against all, if I take, which is this, what it is doing is that it is learning one classifier with between 1 and 2, 3. So 2, 3 is taken as one class, 1 is taken as another class. So it learns a classifier between them. So another classifier it learns between 2 and 1, 3. Another classifier it learns in between 1, 3 and 1, 2. Okay. So if this classifier is more confident that it belongs to class 1, then it will classify as 1. If this classifier is more confident that it belongs to 2, then it classified as 2. If this classifier is more confident that it belongs to class 3, then it will classify it as 3. Right? So this is how it classifies. Suppose let's take another one, 1 against 1. It is also called as all against all. So in this, it learns a classifier, binary classifier between all possible pairs. Right? So what are the possible pairs? 1 versus 2, 1 versus 3, 2 versus 3. These are the possible pairs, isn't it? So once it learns the binary classifier between all possible pairs, it goes for the voting. So it gives, when the new instance comes in, it gives it to this classifier, right? It gives it to this classifier. Suppose if this is predicting it as 1, so the count for 1 is 1. Suppose if this is also predicting it as 1, the count for 1 is 2, right? So the class 1 has got 2 votes so far. Class 2 has got 0 votes. Class 3 has got 0 votes, right? So 2 versus 3, let's suppose it is classifying it as 3. So 3 has got 1 vote now. So the total number of votes, if you see, class 1 is 2 votes, class 2 0 votes, class 3 1 vote. So which label would you assign to this new instance? 2 or 1 or class 1 you would assign because it has got majority of the votes. So that is how it works. So there are different ways that you can extend binary classifier to multi-class classification problem. Brinda ma'am, it is not bagging. Bagging is coming later. I'll explain bagging also is there in the slides. So the other one is the decision tree structure. The model is looking like a decision tree-like structure in which the internal nodes are the decisions that we take on the attributes. So we ask a question about the attribute, whether it is yes or no, whether it is married or not, whether it belongs greater than 80K or less than 80K. So these kind of questions that we ask in internal nodes. Based on these questions, we proceed to the next internal node, next internal node, and so on to the leaf node. And leaf node classifies it as the one of the classes. And this decision tree we construct based on the training data at hand. Once the decision tree is constructed, this is how we test for the new instance. So this is a new instance for which we only know the features, we don't know the output label. The output label is whether he would cheat or not, yes or no. Okay, so given a person and his refund status, his marital status, his taxable income, all this information is known to us. So we have to predict whether he would cheat or not. Okay, so based on this model, the decision tree that we have constructed, let us see whether he would cheat or not. So the first root attribute is checking for the refund attribute. Refund is no, right? For this test instance. So refund is no, you follow this path. Okay, the next internal node is checking for the marital status, whether he is married or not. If he is married, then you follow this path, then it is finally assigning cheat to no. Okay, he will not cheat, right? So that is how the decision trees work. The construction of the decision tree is outside the scope of this session. So if you're more interested in all these models, I'm not going to the details of how we construct a model. Okay, I'm just explaining you the model. If you're more interested about learning the internals of each and every model, we have one FDP coming in next week. So if you're interested, you may register for it. I think 5 more seats are available. So if you're interested, you may register. All right. So that's about the decision tree. So we have seen some of the question from Naman Agarwal is we can use the decision tree for regression problem also. Decision tree regression, that's what they call something. So they also estimate the regression. Diksha madam, the name of, sorry, what is the name of the course for the next week? Name of the course is Machine Learning for Data Science using Python. I think I have already shared a browser in your group. If you have missed it, I can share it with you after this session. I'll share, no problem, again in the group. All right. The next one is ensemble methods, right? So I have just taken one ensemble method, keeping the time in mind. There are multiple ensemble approaches. So ensemble is basically combining multiple models to get a better outcome. So we combine the outcome of the multiple models, right? There are some simple ensembles like voting we have seen in the previous slides, one of the slides. Like for example, you may develop multiple models for the same data set. Okay, so let's say I have a data set D. I give it to model 1, okay, and model 2 and model 3. I build 3 different models. Like model 1 may be SVM, model 2 may be decision trees, model 3 may be logistic regression. So I develop multiple models using the same data set. So when the new instance comes in, I give it to all these models. I give it to this model. Let's say SVM is classifying it as 1. I give it to decision trees. Let's say decision trees also classifying it as 1. I give it to logistic regression. Let's say it is classifying it as 0. So what is the majority of the models classifying it as? Majority of the models classifying it as 1. So therefore, you assign a class label 1 to it. If it is a regression problem, you take average of the individual predictions. So this is simple ensemble. We call it as voting or average. Right. There are also some other simple models like stacking. If you are interested, you can explore stacking. Okay, output of one level models is given as input to the another level of models. Okay, so your models are stacked together. Outcome of this is given as input for the another one. So this we call as a stack. So this is simple ensembles. So in all of these ensemble techniques, we use the same data set and give it to the multiple models. Okay, now the question is, can we use the same model with the different data sets? Okay, so with that idea, the bagging came in. Okay, so the bagging concept uses multiple data sets with the same model. So it doesn't use multiple models like SVM or decision trees or logistic regression. It fixes the model to either SVM or decision trees, whatever it is. To one model it fixes, but it generates multiple data sets. Okay, so we have the original data set from which we generate multiple data sets. With each one of these data set, we learn one of the classifiers or any model, right? Like for example, if the underlying model is SVM, okay. So with this the original data set, we generate multiple data sets. How do we generate? I'll explain. But we generate multiple data sets like D1, data set 1, data set 2, so on. Okay. So I give it data set 1 to the SVM and it will learn SVM 1. I give the data set D2 to the SVM, will learn SVM 2, and so on. Okay, and the output of all these multiple models are combined together to get the output. Now the question is, how do we get multiple data sets from a single data set? Right, that is the question. We generate multiple data sets from the same data set by sampling method. We take the sample, we follow the sampling with replacement method. Right. So I take, like for example, if the data set has 10 points, let's say 1 to 10. Okay, so randomly I pick one sample out of 10. Right. Let's say it is 1. I replace this 1 back to this data set. I pick another sample. Right. Let's say it is 2. I replace this back to the data set. I pick another 1. Right. Let's say it is 1 again. Like this, I pick 10 samples. So when I pick 10 samples with replacement method, then some of the duplicate records I may get, but the data sets that I will get are different from one another. So I may get different 10 points here, different 10 points here, different 10 points here, and so on. So these data sets are sufficiently different from each other. Therefore, the models that we will get are different from one another. Okay, so in each one of these models, there will be overlapping, but they're not exactly same. The D1 and D2 may be some overlap between them, but they are not exactly same. So the data sets are unique, not the data samples. Around, 63% of, studies showing that around 63% of these unique samples you may get in each one of the data sets. So therefore, they are sufficiently different from one another. So the models that we get also different from one another. All right. Is that clear? Okay, right. So this is the bagging approach. There are some advanced ensemble methods, boosting, ADA boost, gradient boost, XZ boost. There are various techniques, but we are not going to discuss all of them. No, I'm just giving you an example. It's not the numbers from 1 to 10. Suppose if you have some 1,000 instances, then you can have a numbers between 1 to 1,000, right? So when I'm picking number 1, I'm picking that instance, one instance, a second instance, that row, first row or second row or third row. That's what it means when I say I'm picking 1, right? Is that clear? Is that clear? Yeah. Right. So, so let us stop here and go to the implementation part. It's already close to 7:50. I may take more than, around 10 minutes more, so if that is okay with you. So let me finish this polynomial regression part first of all. Then we'll go to where is that? Day 1, right? Earlier yesterday. Okay, so linear regression model we have implemented because the polynomial regression is not much different from this. Let me complete this polynomial regression. Then I have already written the code for the other things. I'll quickly go through it because typing takes a lot of time. So let me okay, so this is the linear regression model that we have done, right? Linear regression. Correct. So I take a different data set here. The data set that I have shown you in the slides, sin 2 by x. Right. So I'm writing a function to generate this data set using sin 2 pi x, generate data set. It takes some number of samples as the input. Samples, okay. Right. So x should be randomly generated, isn't it? So I'm just taking np.alias of np.rand. I'll explain you this. Let me quickly type this random.rand and samples. So what am I doing here? I'm just randomly generating number of samples. Suppose number of samples is 10, then I randomly generate 10 numbers. Okay, from the normal distribution. Random is normal distribution, right? Which is there in the NumPy library, right? So I'm taking absolute value of this because I want only positive numbers. Okay, right? And when I randomly generate numbers, this may be in any range. So I'm just normalizing it between 0 and 1, but dividing it with the maximum 1 value of this. Okay, I'm just bringing it to a certain range. And then I'm just sorting them to have them in as to have a beautiful curve, not zigzag curve. Okay. I'm just sorting them. Now this is my x. I've got x which is randomly generated. I just sorted them. Okay. So this is x. Once I get x, what next? I have to generate y. Okay. From the underlying model. What is the underlying model? Underlying model is 2 pi x, isn't it? So the model is sin 2 pi x. That's what we have seen in the slides, right? The underlying model is sin 2 pi x and some random noise added to it. So I'm taking sin function from the NumPy library np.sin and then I'm giving 2 pi. How do we get pi value? From NumPy library I can get pi value np.pi and x. Right. So sin 2 pi x, right? And then I have to add some random noise to it, right? So I'm just adding some random noise to it. np.random, not rand. So here I'm taking uniform distribution. Okay, divided by some 100. I just want to add some small noise to it. That is why I'm dividing it by 100. If you want to add more noise, you can just divide it by 10 or you can leave it as that. Okay, so this is my y. Okay, right. I'm just you can just bring them in a proper format. Right. To have them in as like column vectors. Right. So this is just generating the data. Data is like the curve that you can, I'll show you that. X comma y. Okay, so I'll show you that. So let me show you scatter. Where is this? Right. So let me call this here. X1 y1 is equivalent to generate data. I'm just calling that function data set of 100 points I want to generate. I'm just plotting them. What is the problem? Generate data set is not defined. Generate data set. Oh, I didn't execute this one. Right, you can see that, right? This is how you can, it is generating the points, right? Right, so this is how it is generating the points. Now I've generated the data set, the kind of data set that I want. What is the additional thing that we have to do in case of polynomial regression? I have to generate the new features. New features are x square, x cube, and so on. isn't it? So to generate the polynomial features, there is a function in the sklearn. So I just import that function to generate the polynomial features from sklearn dot preprocessing. So if you want to do any preprocessing, there are various methods in sklearn dot preprocessing. You can check it out. So this polynomial feature generation is one of the preprocessing type. Polynomial features. Okay. So for any number of input variables, it automatically generates the polynomial features given the degree of it. Okay. So I've just imported this, and I write a function for this to generate the features. Generate features. I'm just writing my own function. So the input for this is x and degree. Right. So I just call this function polynomial features is equivalent to polynomial model is equivalent to polynomial features with the degree specified. Okay. So degree is whatever I get as the input. Now I have to apply fit transform on this to get the polynomial features. Right. So poly dot fit transform of x. So what it is doing, it is adding, like if the degree specify x square, sorry, degree is equivalent to 2. So it add x square also to it. If I specify degree, then it adds x square, x cube, and so on. Right. So it automatically generates. So I just have to return this. Right. So my data is ready. Right. So let me execute this. I've just defined this. So now what is next? I just have to call this function, isn't it? So start here to implement the polynomial integration. So I have to initialize the number of samples to generate the data set. Let's say I want to generate 100 samples, and I also have to define the degree. Degree is, let's say, this 2. You can also give 1. 1 means linear regression. So let's start with 1. Okay. So now I generate the data set x comma y is, I have already implemented generate data set. Let me call that. So generate data set. So could you see my screen clearly? No problem, right? Any problem? Are you following me? Following me? Okay, good. So I generate the number of samples which returns x and y, as you can see here. So this is the x and y it is returning. Right. So once I generate the data set, I also have to generate the polynomial features. So I call generate features. So this returns x poly to me, right? So generate features x, and I also need to specify the degree, right? So this is the degree I'm passing, it returns me x poly, right? So once I get this x polynomial, I have to divide the data into training and testing. Right, let me copy it from here. So let me copy all this. Right. So rest of the thing is same. So I just generated the features. So now my x is x poly. So that's the only difference. Instead of x, I'm just calling x poly. And linear regression, one thing that you need to is normalize equivalent to true, because when you generate the new features, they're in different ranges. So you want to bring them to the same scales. So we're just adding normalization equal to 2. Alright. So this is not linear regression model. This is polynomial regression model because we are passing x poly to it. Okay. So polynomial regression. polynomial regression. We predict for the test data and we just print this. Okay. So, n samples is not defined. N sample. Okay, so you can see MA is 0.4, right? So if you want to visualize how is it looking like, let me plot this for you. I just plot so let me just feed the data to total data. So okay, X poly and Y. Okay, so and then I just predict for X poly. Okay. Now let me plot this. Plot dot scatter of X, Y, and I just plot X and Y predict, isn't it? Y predict, not Y. And I just use red curve for this. Sure. Right. So when D is equivalent to 1, this is how it is looking like, right? So you can see this D equivalent to. Right. So D equivalent to 1. Okay, so let me bring all this here. Whatever else. Okay. Okay, so let me, not a problem. Not a problem. So this is how it is looking like. So let me change the degree. Let me add some labels to it so that we can have a better understanding about this. Plot X label is what? X label is X. And what is Y label? Y label is 2 pi X. 2 pi X. And what title that we give? I suggest some title. Polynomial regression. Okay. So right. Let me try different degrees. Let's try to. So the model is looking like this. Let me try 3. See, the model is close to the original model. Let me try 4. Okay, it's even more closer. Let me try 10. Okay. So I'll show you one thing. Let me take only just few instances. So you can see this is overfitting to the data, isn't it? So another solution to the overfitting problem is increasing the dataset size. So if you increase the dataset size, this problem is eliminated, but it may not be possible always. Right. So you can see this. MA we have got is 51. Right. But if you see the triangle, is perfectly go through each and every data point. Okay. But whereas if you see this testing error is very high, as you can see there. Right. So now I'll show you the same thing. I've increased it to 1000. You can see the perfectly going through each and every data point. The same degree of the polynomial is not changing. Right. I've just increased the number of samples. And MA error you can see 0.002 for the test data, whereas earlier it is 54. Okay, so that much difference. So have you got my point? All right. Is that fine? Any queries so far?
So please share these codes.
Sorry?
Please share these codes.
Okay, sure, sure. You wanna try it, huh? Let me share this from here onwards, right? You want me to share it now or later? Now only, right? So I'll take 10 more minutes. Is that fine? Yeah. Okay. So similarly, you can also import the same thing. I mean, models like lasso from SQL dot. I am not going to demonstrate them in detail, but you can explore them from SQL dot linear model. Yeah. Import lasso or ridge or elastic net. Okay, and see what is happening. Okay, so these are the three models that we have discussed now. I'll share the code with you probably. I think I must be having somewhere. Let me copy it for you. Linear regression. Okay, I'm not going to execute them, but let me copy them for you so that I can share it with you. Okay, this is lasso. And similarly, you can have a ridge. You can try them. I'll copy to you just now. You can try them. You can also copy elastic. Right. So you can try on these models also. Okay. All right, so that's all about the regression. We've tried various models. Now let me go to the classification and demonstrate the different models that we have discussed. Okay, so let me close this. So I'm directly going and explaining it because typing is taking a lot of time. So I've already typed them. You can just go through them. You can just go through them quickly. So the pattern is same. We import the model. So logistic regression model from SQL linear model. I'm importing logistic regression model, and then I'm reading the data. So this time I'm reading the data from .csv file. So I'm reading the data, and just to show it to you, I have printed first few records, first 5 records. So this is how the data is looking like. Features for this is self-study daily, tuition monthly, and the target value is whether he will pass or fail based on his self-study and his tuition monthly, right? So this is how the data is looking like. Now, once I read the data, so I read the data using Pandas framework, right? So data frames, I've read it in the data frames. So there is a question, I'll take up that later. Let me finish that and come back to it. I think it's not relevant to this. I mean, whatever I'm discussing right now. So I'll take it later. So I've read the data, which is in the data frame. Okay. So now I have to prepare the data in the required format. So observe the pattern. The pattern is same. In linear regression also, we have followed the same pattern. We have loaded the data. Once the data is loaded, we have prepared the data in the required format. And after that, we have divided the data into training and testing. After that, we feed the model to the training data and test it, predict for the test data. So the pattern is same here also. So we load the data here. Once we load the data, prepare the data in the required format. So because it's a data frame, I'm just dropping out the last column and the remaining columns is taken as X. So X is the feature vectors. And just the last column, I've taken it as Y. So I've just dropped out pass or fail column, the last column. So this last column, and the remaining columns are taken as X. Just the last column I'm accessing and taking it as Y. So I've got the data in the required format. So once I get the data in the required format, I just have to split them into training and testing. So I've called train test split to divide the data. So here the test size is not mentioned. If I don't mention any test size, by default it takes it as 20%. Okay, so it is written in X train, X test, Y train and Y test. Right. So once I divide the data into training and testing, I have to call the model and feed the model for the training data. So I'm calling the model logistic regression model, as you can see here, and then I'm just feeding it to the training data. Okay, X train and Y train I'm passing it. So once I get the model, I have to predict it for the test data. So this is what I am just calling the predict on the test data and I get Y prediction. So what next? I had to evaluate the performance of a model. For that, I need to import sklearn matrix. So I've imported sklearn matrix. Then sklearn matrix, I'm just calling the accuracy score. So there are different evaluation metrics. I'm just calling accuracy score on the test and prediction. I'm just multiplying with 100 to know the percentage of accuracy. So accuracy percentage is 100% here. That means for this data set, logistic regression is working well done. Right? So the pattern is common. So you can just, it's very easy once you get the pattern. Right? So the logistic regression, then SVM. So let's go to SVM. SVM. So again, the pattern is same. You import the model that you want, sklearn.svm, you import SVC. SV is the support vector classifier. Okay, and these are the different metrics. I'm just importing classification report and confusion metric, and the rest of the things you know. So I'm reading the data set. So this is the data set that I'm reading from .csv file. Right, I'm just showing it to you here. So this is how the data is looking. There are 4 features and 1 target value. And I'm preparing the data in the required format by dropping out the last column. I'm taking them as X. The last column itself, I'm taking it as Y. Right? And I'm dividing the data into training and testing. After that, I'm building a model. So I'm calling this support vector classifier SVC by passing kernel equivalent to linear. So I just want to show you linear SVM to you first, then some some kernel SVM later. So if you don't specify anything, by default it takes RB of kernel as the default kernel. Okay, so if you want linear kernel, linear SVM, then you set the kernel to linear and fit the data and predict for the test data. Right? So predict for the test data. You're fitting it for the training data and predicting it for the test data. SVC classifier, you got the Y prediction. You call this different evaluation metrics that you have imported, that is confusion metrics and classification report, by passing Y test and Y prediction to it. So Y test is the ground truth, Y prediction is the prediction, the model's prediction. The confusion matrix you can see. Confusion matrix means how many values are confused. If you see 154 of the class 0 instances are classified as class 0. It means this 154 is the correct predictions. Similarly, 119 class 1 instances are classified as class 1. So this 119 is also correct. So all the elements through the diagonal are the correct predictions. So if you see this 0 instances of class 0 are classified as class 1. It means no wrong prediction there also. But here there is some wrong prediction. Only 2 instances of class 1 are classified as class 0. 2 instances of class 1 are classified as class 0. So there is a wrong prediction here. 2 instances are wrongly classified out of all this. Right? And these are the different metrics. Precision recall. This is all displayed in the classification report. Right? And suppose if you want to set, if you want to do cross-fault, k-fold cross-validation, you can do using cross-validation score by setting the hypothesis as support vector classifier. This I have already shown you earlier. And if you want to use a different kernel, that is also possible. For this, I have used a different data set. Acha, this is another way that you can read the data set. If you have a data set at some URL, like I have an iris data set at this URL, I can directly read from it. Okay. So for that, I use read CSV from Pandas framework. I directly pass the URL and column names. Okay. So I prepared the data set and divided the data set into training and testing. And this is how the data is looking like. 4 features: sepal length, sepal width, petal length, and petal width. So this is a flower data set. 4 features are sepal length, sepal width, petal length, petal width. And there are 3 classes: Setosa, Vazina, some other flower name. So you can use polynomial kernel, you can use RPF kernel, you can set whatever the kernel that you want. Okay, so this is the kernel. I'm just fitting it to the training data, predicting for the test data. And this is the classification report. You can see the classification report is very good. Okay, only these 2 instances are wrongly classified. These 2. Otherwise, everywhere it is correct. Precision is also almost 100. Right. Similarly, you can use multi-classes view. From sklearn.multiclass, you can import one versus rest classifier. The procedure is same, fit predict. Or you can import one versus one classifier. So there are these are all from sklearn.multiclass. The procedure is same, dividing the data, then fit, then predict. That's all. Right. All right. So any queries so far?
Could you explain how, sir, could
Yeah.
you explain how to import from URL?
How to import from the URL?
Yeah.
Okay, is that the question? Yeah. Suppose if you have a data at some URL, like for example, I'll show you this. Where is this? Okay. Yeah, this is the. So I have the data set at this URL. Let me show you that. Let me access that data set. Okay. So okay. It might have been downloaded. Yes, you can see that, right? This is downloaded when I type. It means I have a data set in that. Right. So when you know that it is at some URL, you can directly use that URL. Like for example, so this is the URL that I'm passing, and you know the column names. I know the column names: sepal length, sepal width, petal width, class. Right, this is the order. Right. So read CSV is the function that we use from the pandas library. PD is the pandas library, and I pass the URL to it and just names as the column names. Okay, so it directly returns that data set to me, and from this I just drop the last column, and remaining columns are taken as X. Just the last column is taken as Y. Okay, that's all. Very simple. Is that clear, Karthik?
Yes, sir. Sir, could you explain why we are taking only last column as X? That is little bit confused.
So last column indicates the target value. That is why I'm just taking it as Y. Y is the target value, right?
Yeah. Understood.
Yeah, so the last column indicates the class label. So you can see it here, right? This is how the data is looking like. The first 4 are the features and the last column is the class information. So that is why the last column I'm taking it as Y. The rest of them I'm taking as X. X is a feature vector, set of feature vectors. Understood, Karthik? Any other query?
Okay, sir.
Yeah, actually your voice is too low, so I am actually not getting what you're speaking. So I hope it is fine. If you have any other query, you can ask. Any other query? All right. Okay. So that's all we've done with SVM also. So 2 more left: decision trees and bagging. Quickly go through them. So let us try to quickly go through them. Decision trees. One more thing. Bagging. So I just want to show you the libraries, that's all, but the pattern is same. So bagging, for example, from sklearn.ensemble, you can import the bagging classifier. Okay. So once you import this bagging classifier, you are importing the dataset here, then preparing the dataset here, then dividing the dataset here, right? You're dividing the dataset here, then you're calling the classifier here by calling the base estimator. So SVC is the base estimator here. The number of estimators you are passing, it means that how many datasets you want to take, isn't it? We are taking multiple datasets is giving to the same classifier, isn't it? So 5 number of estimators means 5 datasets we generate and give it to SVM. So it gives 5 SVMs. And we just feed it to the training data and predict for the test data. And this is the classification report that I'm printing. Right? So very simple. Similarly, decision tree. Okay. So from the decision tree, this is the library. sklearn.tree. We import the decision tree classifier and then we read the dataset, we prepare the dataset, then split the dataset, we build the model and we prepare the test. Right. Right. So if you want a different criterion, I mean, there are different criteria to select what is the root node, what is the internal node, and there are different criteria. By default, the criteria is Zini index. If you want to take a different criteria, you can pass them as an option for this. Okay. Also, if you want to visualize how the tree is look like, how the tree looks like, and this is how you can tree dot plot tree, and you pass the classifier to it. Classifier is the model that you are getting here. So CLF you are passing, and tree is the library that you are importing from sklearn. Importing tree, from that you are accessing plot tree. You're just passing classified, and this is how the tree is looking like. Okay, so that's all. If you have any queries, I'll take. Otherwise, we can wind up. Okay, it's already delayed by 20 minutes. So if you have any queries, I'll quickly take. Otherwise, we can wind up. Any queries? All right. Thank you very much. Happy learning and good night.